Okay, good morning and welcome to our series of lectures on understanding Higgs mechanism. Yesterday, the last class, we discussed the Lagrange for fermions, and the Lagrange for fermions we discussed as that comes about to I of C psi bar minus L C square. This we have derived and we found that this is the Lagrangian for the fermion field. But this Lagrangian remains invariant if the field function psi is transformed to a new field with a phase factor to the power I theta, where theta is constant. The Lagrangian remains same when the field function is transformed by constant phase factor. The Lagrangian remains invariant. Now if you take this theta not as constant, but suppose you take theta as e to the power I, e power I theta, x dependent upon x denotes position and time. So if the field varies, it is transformed, and this is the phase factor, and this phase factor is not constant, but it depends upon the position and time, then the Lagrangian is not does not remain invariant. Now we have also found that to make the Lagrangian invariant, we have to add another field A. It's called electromagnetic field, which transforms as A plus minus some phase factor plus lambda times lambda. So that some yes, A plus d mu lambda, where lambda was minus hc by q theta. So we have found that if we add a new field to this Lagrangian, that the new field is due to the electromagnetic interaction, then the Lagrangian becomes invariant, and we arrived the new Lagrangian as I cross C minus LC square, and the new Lagrangian which we have added, the new part factor which we added in the Lagrangian, so that it becomes invariant, and that is minus q psi bar gamma mu a mu psi, where this is the kinetic energy part of the fermion field, this is the potential energy part of the fermion field, and this is the interaction between the fermion field and the electromagnetic field, where q is the coupling constant. So the constant by which these two fields couples. So this is our Lagrangian, which remains invariant by the transformation. If you transform the field, fermion field psi, by this phase factor on this Lagrangian, you will find that the Lagrangian remains invariant. But this is not the complete picture, because although we have included here the interaction of the electromagnetic field with the Fermion field, we have to have a Lagrangian of the electromagnetic field also. And what's the Lagrangian of the electromagnetic field? The complete Lagrangian must contain part, the Lagrangian from this, means we have the complete Lagrangian must be Lagrangian from Fermion field plus Lagrangian from electromagnetic field plus interaction part. We have taken the interaction part, but this must have Lagrangian of the electromagnetic field also. But the electromagnetic field is a boson field, a vector field of spin 1. So the Lagrangian for spin 1 particle, the Lagrangian for, we have a Lagrangian for spin 1 particle. We have Lagrangian for spin 1 particle provided by Alexander Prokop. So the Lagrangian for spin 1 part is 1 by 16 pi f mu f mu 1 by 8 pi n c by h cross square a mu. So this f, where f mu was the electromagnetic field tensor, and this was delta A nu by delta x nu by delta A nu by delta x nu. This we have already worked out, that this is the electromagnetic field tensor. This is the variation of the electromagnetic field with space and time. So this part, the first part of the Lagrangian, we have the Lagrangian, oh sorry, this is minus here. Small minus. So this part gives you the kinetic energy part, because this gives you the variation of the electromagnetic field with the space and time. So this is the kinetic energy part, and this is the potential energy part. This is the square of the field. This is A square. So it means this is the kinetic energy part and this is the potential energy part. Now we want to find that we have assumed a transformation for A. We have just, I just run that transformation here. And the transformation for A was that A transforms to a new A with some tell me of some constant. It's not constant, but it is minus xc by q theta. And theta depends upon space and time. So even we have assumed that here A transforms to A plus del mu lambda. Then this Lagrangian was invariant, gauge invariant. So we will try that transformation here also for spin 1 particle, Lagrangian for spin 1 particle, and see that this transformation, whether this transformation leaves the Lagrangian invariant or not. So, okay, I should rub this one. we have the Lagrangian. I'm writing this one again here. Minus 1 by 16 pi f mu of f mu means okay. Minus plus 1 by 8 pi LC y cross square A nu A. So this is our same equation here. Now we want to find that under the transformation how f mu transforms. So suppose f mu is transformed to a nu f mu. So this is the transformed part. F mu is this. It means delta mu A mu plus d mu that. Okay, and that this is the n so this will say f mu means derivative with respect to nu and then with respect, and a is transformed from a nu to a, this values. Now next this one, del by del x nu, del by del x nu, del by del x nu. Now minus del by del x nu, so del nu, and a mu is transformed to a mu plus a mu plus delta mu. Here it is del by del x mu. So it is del by del x mu and del by del x mu. So if you write this, this will be a mu plus minus this is the same thing. This is the derivative of lambda with respect to nu and then derivative of lambda with respect to d mu. This is the derivative. So it's the same things. So this will cancel out and you are left with del mu a mu minus del mu a mu, which is again this is the same value. So it means under this transformation of field A, this part remains invalid. Now what about this part? So that part we have a nu a nu. Now a nu is transformed to a nu plus delta this A is transformed to, because A is transformed to A plus delta mu. So in this way, A nu is transformed, and the this transformed. Open the bracket, you will get 2 times this, 2 times A nu plus this. So it means A is not invariant. This part, potential energy part, is not invariant, but it comes out to be, these are extra terms. So this is actually this last part, and then this is kind of, say, del square. This is the extra term to the field which we added to the A. This is the square of the variation of this square of this is the variation, means the variation with respect to space and time. So this is the space and time variation of the field which is added to the automatic field. So it means this contributes some kind of kinetic energy of the added part of the field. And this term so we will discuss this part. Substitute here, the potential energy part becomes this much, 1 by 8 pi. So the potential energy part, if you ignore this small variation in the kinetic energy of the added field and concentrate only on this side, because if we remove this one, still it's not invariant. So what about this? So if you substitute this A nu here, you have this part, 1 by 8 pi MC square, MC by 2 times A nu delta nu. I am considering only this part. Okay, okay, maybe substitute the whole part. Okay. Substitute the whole part. Now, this is the added quantity here. Apart from this value, this is added to this field, electromagnetic field of spin 1 particles. This is called Lagrange for spin 1. So we want this to be 0 for the Lagrange to be invariant. And this electromagnetic field of spin 1 to be invariant. This part must be 0. And this part must be 0, means either this, it consists of 3 parts. Consists of for this to be 0, either del nu lambda should be 0. If we take this as 0 to make this invariant, it means we are not adding any term to any extra field to A. With this, we are not assuming this. And if we do not assume this, you assume this to be 0, our Lagrangian for the Fermat field will not be then invariant, gauge invariant. So this is ruled out. You cannot take this as 0, because if you take 0, then the Lagrangian for Fermat field will not be invariant. The next part is, suppose A mu is 0. If A mu is 0, electromagnetic field is 0. If the electromagnetic field is 0, it means the interaction part of the Fermat field is 0. It means again the Fermat field is not, remains invariant. It means if there is no field, there is no excitation, no quanta, field quanta. No A0 means no field, means no excitation of the field, means no photon, because the excitation of the electromagnetic field is the quanta which is due to the excitation of the electromagnetic field is called photon, which is no photon. So this is also not acceptable. The only thing which can be assumed to be, for this to be 0, it means we assume m to be 0. If you take m to be 0, this whole thing becomes 0, and then this becomes Lagrangian, becomes invariant. It means m is 0 is only the sensible option here. Hence m0 is the only sensible option left. It means if m is equal to 0, means that theoretically this mass of the boson, which mass of the interacting field, the boson means that those particles which appears due to the interaction of the fields, the field quanta. So it means if we take m is equal to 0, it means theoretically all gauge bosons are spin 1. Theoretically all gauge bosons of spin 1 must of 0 mass. That is why the photon at rest is assumed, the mass of the photon at rest is equal to 0. That is why the mass of the photon at rest is assumed 0. It means our Lagrangian for the spin 1 particle, spin 1 boson particle, will only contains only this part 1 plus u pi f u f. That this is only the kinetic energy part of the electromagnetic field. So we conclude conclusion. if we start with Dirac-Lagrange, if we start with Dirac-Lagrange and impose local gauge and impose local gauge transformation, we are forced to assume we are forced to introduce a massless vector field A mu. The complete Lagrangian then becomes the complete Lagrangian then becomes this is the complete Lagrangian. This includes Dirac Lagrangian minus mc square. This was the Dirac part plus this part, so it's a minus 1 by 16 f mu nu f mu plus that interaction part, so minus q psi bar so in here we have this Lagrangian has three parts. The first part is this makes the complete Lagrangian. This part of the Lagrangian represents fermion. This represents fermions. Lagrangian for fermions. This is the Lagrangian for electromagnetic field. This is the kinetic energy for the electromagnetic field. This is the kinetic energy for fermion and potential energy for the fermion. The kinetic energy of the electromagnetic field, and this is the interaction of the electromagnetic field with the fermion field. So the complete picture looks like this. This represents, if you Feynman's diagram, this will represents a straight line, and a fermion is moving with in space time. This represents by an arrow. This is maybe electron or positron or any fermions. And this represents electromagnetic field part. The electromagnetic field is denoted like this. This represents a photon or spin 1 represents spin 1 part, spin 1. This bosons, spin 1, massless, because there is no mass here, it's only the kinetic energy part, and plus this is the interaction term. Interaction term means if the electron and positron is moving, this interacts, this electromagnetic field interacts, as a result this will change. So this is the interaction part here. This is the fermion interacts with the electromagnetic field, and so they can deflects the fermion is deflected. So this is the interaction of the fermion field with the boson's field. Okay. So it's nuts. Okay.